This is a topic that's sometimes called calculus of variations. That's sort of the classic name for it. And Cookie, are you causing trouble? Okay. Calculus of variations, but all it really is the same idea of derivatives, where so we're going to have f of u plus du minus f of u. That's our df. Is going to be, I'm going to call it f prime of u du. Right? It's the same formula. It's except that now, where u is in a vector space of functions, right? And usually f usually f is a scalar. F of u is just a real number. Okay, so we're going to take a function, map it to a real number. And this is one of the things when I teach 1806, I come back to periodically that vectors are not just column vectors, they're even matrices. You can even think of functions as a vector, because you can take two functions, you can add them. You can take two and get another function. You can take two functions and multiply them, a function and multiply by 2 and get another function. And so a lot of the things you can do in linear algebra for column vectors you can do for functions, right? You can talk about linear operators on functions, like a derivative is a linear operator on function. You can talk about orthogonal functions and dot products of functions and Gram-Schmidt on functions and eigenfunctions. If you do quantum mechanics, you do lots of things with eigenfunctions, right? So it's the same all the same kinds of concepts. You have to be a little bit careful with functions. They can do crazy things that column vectors can't, like they can oscillate infinitely fast, or they can blow up, or do things like that. So if you want to do rigorous math with functions, you spend a lot of time kind of nailing down the space of functions that are not terribly behaved. I'm not going to do that. I'm just going to be kind of implicitly, I'm going to write down an integral of functions of a function. I'm going to implicitly assume that we're dealing with functions where that integral is defined. So that's things like that, right? So let me just do an example, right? So let's do u of x is a function, from 0 to 1, right? X is in 0 to 1. To real numbers, right? It's just here's x equals 0, x equals 1, and u is some function, right? U of x. Right? Right? And let's suppose that f of u, I need to write down something that takes in a function and gives me a number. Well, there are a few ways to do that, but the one that I want to deal with is just integral 0 to 1 of, say, sine of u of x dx. Let's just start with, right? That takes in a function, gives me a number. Technically, it doesn't work for all functions, right? You could have functions where this integral doesn't exist or something like that. So implicitly, I'm limiting myself to the space of functions where the integrals work, right? And what I want to do is find out what is the gradient of f, right? What is f primed also, right? With respect to u, of course, right? So now with respect to a function. Right? And it's going to be exactly the same definition for it to take a derivative. To take a derivative, I just need to linearize. I need to ask, how does f change for a small change in the input, right? Linearize it. And then to get one step further, to get a gradient, I'm going to need a dot product. But let's do this before we do the gradient and the dot product. Let's just linearize, right? So, right? So we're going to take df. We take f of u. Remember, u is a function. By the way, this is sometimes called a functional It's something that takes in a function and gives you a number. But sorry, and here I need f of u plus du minus f of u. And the key thing to remember is that this is a function, u of x. That's a terrible x. And this du here, this is also a function. You could think of it as a small function, du of x. Right? And as I said last lecture, to get some notion of small, we're going to need a norm of a function. But pretty soon I'll have dot products of functions, so I'll have norms as well. So let me sweep that under the rug. But it's just like a little perturbation, right? So you're taking u of x, and you're adding, some arbitrary little change to this. This is a u plus du of x. Right? So you're going to change that function by a little bit anywhere you want. It has to be small, and then so we can drop terms that go like du squared. Right? And so what is this? So this is integral from 0 to 1. I said f was sine of u of x dx. So this looks like sine of u of x plus du of x minus sine of x dx. Right, I'm just plugging that into my f. My f was integral sine u. Right? And I'm going to ask how much does that integral change for a small change in u, and I want to linearize it. Right? So I want to write this as drop every term that goes like du squared or higher. So, of course, the point is, all I need to do is linearize this, linearize the integrand. Right? That thing, sine, oops, sorry, and this is not sine of x, this is sine of u of x. Right? Okay, so I want to linearize this. What is sine? So sine of u plus du, right? That's equal to sine of u plus the derivative, which is cosine of u times du. Right? This is just because this is du is a function, but du of x is just a number. Right? At each x, I have a small change in u of x. So this is just ordinary, 1801. Right? Linearization, or from lecture 1 of this class, right? Or this could be anyway, so this is just a number, ordinary linearization. And then, of course, this term here cancels that term. Right? So what this is integral 0 to 1 of what's left? Cosine of u of x du dx. And this is exactly, this is a linear operator. This is f primed of u acting on du, right? Sorry, and again, I should put a du of x here. Is that clear? If I plug in any function here, any change in my u, this is clearly linear in that. Like if I double this, it doubles the integral. Like if I add two things here, it adds two things in the integral. So this is a linear operator. We're done. That takes du in, and it gives you out a number. Right? This is my df. So once you get used to this as being, the definition of a derivative, right? You can always fall back on this. When u is some crazy object, matrix, function, whatever, as long as it's a vector space, or technically a Banach space, it has to have a norm, then you can define the derivative as the linear operator that gives you the first order change. Right? So, as I said, technically we're dropping terms of little o of du, right? Terms that go to 0 faster than du here. So to make that precise, you need to have a norm. But anyway, this is a function that takes a vector. By function, I'm thinking of it as a vector space, vector in, and gives you out a scalar. So I should be able to write that linear operator, this linear form, as a dot product with something. So for that also, I want a dot product which will give me a norm. So let's just remind you, hopefully you've seen this before in 1806 or some other linear algebra, dot products of functions. Right? So, yes?
Quick question. I guess one takeaway that I have so far is that the derivative is something that lives sort of in the dual space to the thing that is the input to your function.
Yeah.
So
Well, if the output is a scalar, right?
Yeah.
Yes. Yes. So this is exactly something in the dual space. Physicists would call this a bra. Yeah. Yeah, this is a measure. Because exactly, this is the density of that measure. Yeah, absolutely. This takes the measure of that function. Exactly. Yep. So it's all sorts of, you can think of this as a linear form or something in the dual space or a covector, this vector space, right? But I want to say a little bit informal in terms of those abstractions here. And as I said, technically speaking, we have to restrict ourselves to not all possible functions here. They have to be functions where this integral is defined, so they can't be functions that blow up or are not measurable or something like that, right? But that's something that pure mathematicians worry about that physicists and engineers don't, because the functions, basically if this is a physical context, like implicitly you're dealing with functions where these things are defined. Like you only really worry about ruling out those crazy functions if you're doing pure math that's unmoored from reality. So dot products of functions. So if you take a dot product of two column vectors, the standard, there are many dot products, but the standard one, the Euclidean one, is you just multiply the components and add them up. So if you think of two functions, u of x and v of x, on x in 0 to 1, then the sort of the Euclidean dot product, the sort of the obvious dot product, the Euclidean inner product, right, should be to multiply the components and add them up. So the components, if you think of these as column vectors, they're like infinite dimensional column vectors. The components are the values at each point. So basically what you want to do is multiply u of x times v of x and add that up for all the x's. And the analog of adding it up is an integral. That's our u dot v. Right? So we can, and then of course this is not the only possible dot product, but this is the most obvious one, the first one that you typically reach for. Right? So once you have a dot product, then of course we have a norm. So if you want the norm of u, that's just the square root of the integral from 0 to 1 of u of x squared dx. I guess I don't need absolute values here because everything is real right now. If they were complex, I'd be putting complex conjugates over one of these. But so let me remove my absolute values there just for, I don't need them. Right? So and this is and once we have the norm, then that's the precise sense in which we're dropping terms that go like du squared. Right? So we're going to drop terms that go like the norm of du squared and higher, or actually anything higher than linear. Right? And once you have this, now we can find the gradient. Right? Because what was our df? Right? df, which was f primed of u acting on du, right? We said that was integral from 0 to 1 of of, was it, cosine of u of x times du of x dx, right? We want to think of this, just our generic definition of the gradient is when you have something that takes a vector and a scalar out, the first derivative had better be the dot product of the gradient with du. And if we just by inspection, right, this is here. This is our definition of a dot product. So what is the gradient? It's what would I take the dot product with du to get this? Cos of u. Exactly. It's a function. It's just cosine of u of x. By the way, in this context, this is sometimes also called a Frechet derivative. Right? I mean, Frechet derivative technically refers just to this general notion of if you have any Banach space, the Frechet derivative is the linear operator that does this. But most often, you see this coming up in the context of vector spaces of functions. That's where they use that terminology. For everything else, people just say the derivative, right? It really is just the derivative, but that's it, right? This is a gradient. So let's do a more complicated case. So let's do another example, more a tricky example. Right? Suppose that f of u, so we're still going to be functions from 0 to 1, okay? Suppose it's the integral from 0 to 1 of the square root of 1 plus u primed of x squared dx, where this is just the derivative, the ordinary du dx, the 1801 derivative. Right? So this takes a function in, gives you a number out. Clearly, we have to restrict ourselves to differentiable functions now. Right? And what is this? Does anyone recognize this? Can you describe what this quantity is geometrically? So if I have a function u of x, right? It goes here's u of x. What is this quantity that I've just computed here? From first year calculus, there's an important name of this, yeah? It's the length. It's the arc length, right? It's the length of the curve. The arc length of u of x from x equals 0 to x equals 1. Right? That's what this quantity is. If you multiply through by dx, this is basically square root of dx squared plus dy squared. Right? If you take each little line segment here, it's like the length of that little line segment, and you're adding them up. Okay. So now let's think about the derivative. Okay. So now let's take f of u, and we're going to add a little change, du. Right? Subtract f of u. Right? It's always good to just fall back on the definition, the most basic definition, if we're in doubt of what to do. Right? We're going to just add a little change. And what's this going to be? So let's just, it's the integral of, from 0 to 1, the square root of 1 plus u plus du primed squared minus the square root of 1 plus u primed squared. So again, we just think, so now we have to Taylor expand this, but now we have to assume that du is now a differentiable thing, and its derivative is getting smaller and smaller as well, so I can do this kind of expansion, first order expansion. So what is this? Well, it's the, if I have, let's see, if I have like 1 plus, let's see, v plus dv squared, what's the Taylor expansion of that? That's where 1 plus v squared, that's the first term, right? And the second term is the derivative with respect to v, which ends up being v over square root of 1 plus v squared times dv. I kind of went through that a little bit. But this is just 1801. This is just 1801, right? So plus, right? This is this function for dv equals 0. This is the derivative of this, right? So when you take the derivative of the square root, it's 1/2, 1 over the square root, right? But then there's the derivative of this, which gives you a 2v on top, so the 2 cancels the 1/2. Right? So just from calculus, expanding everything to first order in du and also du primed, so dropping anything that goes like anything with a du, whether you take a derivative or not, squared, we're going to just drop. This is the integral of that second term, which is u over square root of 1 plus u squared times, and du, that's primed, right? Divided times du primed dx, right? So this is a linear operator. But it's acting on du primed, not on du per se, right? I mean, the derivative is a linear operator on du, but I'd like to write it directly in terms of du, right? Because I'd like to write it eventually take a gradient and write it as a dot product of something with du. So what I really want to do is write this as a dot product of a gradient dot du, and somehow I have to get a du and not a du primed. So we just saw this in the first hour. If you have an integral and you have a term that has a derivative and you don't want the derivative, what do? What can you do in first year calculus to get rid of a derivative on a term in an integral? Integrate by parts. So what do we do? So that whole thing, let's see, df, there's a boundary term that looks like u primed over square root of 1 plus u primed squared times du at the boundaries, 0, 1. And then you have a minus sign and an integral from 0 to 1 of we take this whole thing primed du, and then times dx. Right? All the u's and du's are functions of x. So to go further, this is it. This is a linear operator. Right? This is now our f primed of u acting on du. This is a linear operator acting on du, and there's no du primes here. This is nice. But it has these boundary terms are kind of annoying. Right? But usually in the context where I'm interested in this, I'm actually going to set some boundary conditions. So in particular, suppose I want to fix the endpoints of my u. Right? And I want to find the curve that has the minimum distance from one point to another. Of course, that's going to be a straight line. Right? But suppose I didn't know that, right? So and this is a simple problem where you know the solution ahead of time, but the more complicated things, you won't know that. So I want to suppose we want to fix let's just even say u of 0 equals u of 1 equals 0, just even for simplicity, right? And so that's and now we want to find the u that minimizes the arc length f of u. Right? We know probably it's a straight line from one point to the other, right? But let's pretend we don't know that. So what we want, if you want to minimize something, what you want is for the gradient to be 0. Right? So we're going to need to take a gradient set equal to 0 in a minute. But if we fix the endpoints, we're going to want du also at 0 or 1 to be 0, right? If we fix them at 0, because if we start with our vector space of u's that are 0 at the endpoints, and we want to look at not all possible perturbations, but perturbations that keep those ends fixed. But if I kept the ends fixed at some other point, still I would want to look at not all possible perturbations. Right? I'd want to look at the perturbations that keep the ends fixed, so that the u is 0 at the ends. So this keeps the endpoints fix, right? And then what happens is that boundary term disappears, right? Our what was it? U primed over square root of 1 plus u prime squared du taken at 0, 1. This is now just 0, right? Because we fixed the endpoints. So now df is just integral 0 to 1 of u primed over square root of 1 plus u prime squared primed times du dx. So our gradient is just this thing here. Right? It's the thing we're taking with the dot product of du with to get the solution. So it's just u primed over square root of 1 plus u primed squared primed. Does everyone see that? So this df had better be the dot product of grad f with dot grad u. I integrated by parts. I turned my u primed into a du. I set boundary conditions to fix the boundaries, so the boundary terms disappeared. What I have left is just a dot product of this with du. So I can think of this as the gradient, right? And if you're at a minimum, it's the same, for the same reason as in 1801 and 1802 and so forth. At a minimum, the gradient has to be 0. Because if it's not 0, you could move in that direction and make it bigger, or move in the opposite of that direction and make it smaller. Right? So this has to equal 0 at a minimum. And so now, I need to work out, okay, now it's a little bit of a calculus exercise. Right? What is the derivative of this thing? Okay, so now it's quotient rule, right? So this is going to be quotient rule. Right? So in the quotient rule, on the bottom you get that denominator squared, so you get 1 plus u primed squared, the square root squared. On the top you get the derivative of the top, which is u double primed, times the bottom, square root of 1 plus u primed squared. And then minus the top times the derivative of the bottom. And we just did that. The derivative of that square root is, in fact, u primed over square root of 1 plus u primed squared, I think. Hopefully I'm not making any mistakes here. Okay, so now if I want to put this over, let's simplify this a little bit. This is 1 plus u primed squared. I'm just going to put a 3/2 on the bottom. So I'm going to pull this term and put it on the bottom. So I'm just going to multiply and divide by that square root. And what you get is a u primed times 1 plus u prime squared minus u prime squared. Right? I'm just simplifying this a little bit. The second one? No, that's because this came from u prime times u primed. This one is u prime. There? That came from this square root. I multiplied the top and the bottom by square root of 1 plus u prime squared. The second term? What's that? So wait, this term, or are we talking about the right term or the left terms? This one here? Sorry, what is this? You're saying this term is wrong? Did I make a mistake? Yeah, so was this term correct? Oh yes, thank you. Oh, good. Yeah, because that's going to screw things up. Okay, so yes. Okay, so good. Sorry. Yes, you're right. The top is not even that. It's u double primed. Good. Okay, I knew something was supposed to cancel here. Good. It's actually u double primed times u primed, right? Okay, good, because it's the derivative of a u prime squared. It gives you a 2 u double primed u primed. The 2 canceled the derivative from the square root. Good. Good. I'm missing a u double primed there. Good. I knew it was supposed to simplify. I was a little worried about that. So now this term cancels this term. And what you get is just u double primed over 1 plus u prime squared to the 3/2. And this is supposed to equal 0, we said. So the only way you can 0 is if u double primed equals 0. And that's a straight line. Right? So what we've just derived is that the shortest distance between 2 points is a straight line. Okay, of course, you knew that. Right? But let's do a generalization. Okay, so let's say f of u is an integral, right, from a to b, right, of some other function. Let's call it capital F, right? It may depend on u, it may depend on u prime, it may depend on x, right? This is a functional. And then what is df? Right? So df is f of u plus du minus f of u, right? So now what are we going to have? So there is going to be a term that looks like partial f partial u. Right, this is an ordinary 1801 partial derivative. I'm assuming u is a number. I guess it could be a vector or something like that, but let's just keep it simple. Times du. There's also a term that looks like partial f partial u primed times du primed times dx. Right? And this sometimes confuses people. It's like, how can if I take the derivative with respect to u, keeping u prime fixed, because obviously u and u are related. It really means the derivative of f with respect to the first argument, right? Right? This is the derivative of f with respect to the second argument, right? And then you plug in u and u prime afterwards, right? So it's just doing exactly the same, and you're doing much like this in homework, but I'm skipping a couple of steps here, but right? This change, there's a change that comes from the first term, like we did on the first example, a sine of u. There's a change that comes from the second term, like in the second example, right? And you have to add them up. But now you integrate by parts. Right? And on the du prime term, because we don't like having du primes. And so you get partial f partial u primed times du at a, b, And then we have a plus an integral a to b. And then there is a term that looks like df du. And there's another term that looks like, with a minus sign, df du primed multiplying du times dx. Again, du is my small change. It's a du of x, right? I'm just suppressing all those. And this term, we're going to set to 0 if the endpoints are fixed of u are fixed. So if we keep u fixed at the endpoints, then we're going to only allow changes, du's, that are arbitrary functions, but at the endpoints they have to be 0. And so what you get is this term here is the gradient. This is a grad f. Right? This is a dot product with du, and so I can write this out. So this is, so grad f is df du minus df du primed. And we set this equal to 0 at an extremum, at a minimum and maximum. And the result, this is, we set this equal to 0. This is some differential equation. It's an equation in U. Right? It involves, and it's actually a second order. Right? Because you started out with u and u primed in your f, but when I take this derivative here, I'm going to get some u double primed terms. Does anyone know the name of this differential equation? Has anyone seen this before? Euler-Lagrange equations. So these are exactly the Euler-Lagrange equations. Where did you see Euler-Lagrange equations before? Optimal control. You also famously see them in advanced mechanics, like 806 or 808. I don't know what the number is these days. Where this is there's something called the least action principle, and you can write down the equations of motion as minimizing some integral, and you get these Euler. Instead of Newton's laws, you get as a different way of getting Newton's laws. You get these Euler-Lagrange equations. They're really nice because they let you write down basically Newton's laws in like really weird coordinate systems pretty easily. Yeah, so there's a famous example of the Euler-Lagrange equation that everyone gives, which is called the Brachistochrone problem. Has anyone heard of the Brachistochrone problem? Yeah, one person, a couple of people, right? So this is a famous problem from, I think, the 18th century, right? So suppose you have a mass falling down a slope, just sliding down a curve with gravity, right? So it's going down this curve like a ramp, right? With no friction, right? Just slides down. And you go, starting here, you're ending up here. And the question is, what shape should this ramp be to get down as quickly as possible? Should it be a straight ramp? Well, or should it be like this? You can pretty easily see this shouldn't be like this, because then it'll start out going very, very slowly and then go, right? A straight ramp, or should it go down very steeply and then flatten out, right? If it goes down very steeply, it'll get going up, get a good head of speed pretty quickly, but then it has a longer distance, right? The straight line would be the shortest distance, but it's not the highest speed. And so it was a famous problem to find, called the Brachistochrone problem, to find the curve of this ramp that minimizes the time. And it's exactly an integral. You can write down this, and you write down a differential equation. You can solve it to get this curve. Unfortunately, the differential equation you get is rather nasty. It is solvable in closed form, but like it's nothing I would ever assign as a homework problem in 1803, for example, right? So it turns out the minimum shaped curve is called a cycloid. It's like it's the curve that if you have a wheel rolling and you attach a pen to one spot on the wheel, and as it rolls, you mark out like the curve that wheel traces out. That's the shape that you get. So it's a famous. So I'll even write that down. To Google example. Google the Brachistochrone problem. brachistochrone problem. That's one example. Another example would be Google the principle of least action. That's how you get the Euler-Lagrange equations in mechanics. So great example. But it lets you turn these things into differential equations, right? But what you're really doing is just taking the gradient and setting it equal to 0. And it's just you have to understand, okay, functions are a kind of vector. I can still talk about linear operators on functions. I can talk about dot products of functions. So this linear operator is exactly for the change. I can take the derivative just is the linearized change in the output in this integral. And if I do a little bit of algebra with the integration by parts, I can write that as an integral of something times du. That's a dot product in a generalized sense. So this thing is a generalized gradient. That you set equal to 0 if you want a minimum or maximum. Any questions? Right, so and I'll put up some references as well on both the what Frank talked about. We have some papers and other reviews and things on adjoint methods for ODEs, and there's lots of papers and books on this Euler-Lagrange equations. And the traditional topic for deriving these Euler-Lagrange equations is calculus of variations. That's what it's called, or variational calculus. But it really is just taking now that we've generalized the notion of derivative, it's just it's the same notion. It's nothing really new. It's just applied to a new vector space. There's a beautiful, beautiful book by Gelfand and Shiloff that I'll put up a link to on calculus of variations. I really like it. It's one of those things that starts out, chapter 1 is accessible to a freshman, and then it gets more and more advanced as it goes along. But it's a very, very slim book, like 150 pages or something like that.